Hi, my name is Tim Middleton. I am a software engineer with the Coherence development team here at Oracle. Welcome to this screencast which covers an overview of federation and persistence when using the Coherence operator. In this video, we will provide a short overview of the Coherence operator, outline its support for federation and persistence, as well as show you a demonstration of these features. What is an operator? An application-specific controller that extends the Kubernetes API to create, configure, and manage instances of complex applications. The Coherence operator is an operator that allows users to create, configure, and manage coherence clusters within a Kubernetes environment. What does the Coherence operator provide? It provides the ability to easily deploy, run, and manage coherence within a Kubernetes environment. It provides integration with common components used within Kubernetes, Elasticsearch, FluentD, and Kibana for log capture and analysis, and Prometheus and Grafana for metrics and monitoring, which is available with the imminent 12.2.1.4 release. Allows you to override and customize your coherence deployments, allows safe scaling in or out via Kubernetes with no data loss, allows you to access the cluster via Coherence Extend, ensures that Coherence is aware of Kubernetes zone information to provide Coherence cluster high availability, allows you to use persistent volume claims to support active persistence, and provides application deployment by a sidecar container. The Coherence Federated Caching feature is used to link multiple clusters so that cache data is automatically synchronized between these clusters. Typically, these clusters are geographically dispersed and can provide redundancy, offsite backup, and multiple points of access for application users in these different locations. The Coherence operator provides full support for federation between coherence clusters in separate Kubernetes clusters when using Coherence version 12.2.1.3.3 and above. Coherence persistence is a set of tools and technologies that manage the persistence and recovery of coherence distributed caches. By default, when you enable persistence in the Coherence operator, it will create a Kubernetes Persistent Volume Claim to store the active and snapshot data. You can manually specify the volumes, allowing you to specify different storage types. For example, if we are using OCI or Oracle's cloud infrastructure, the default storage type of the persistent volume claim would be block storage. This is fine for the snapshot location, but active persistence requires the lowest latency possible and would benefit from a different storage type such as NVRAM. This can be configured while installing the operator. In this demonstration, we will show how to configure, operate, and verify federation between coherence clusters when using the Coherence operator. Typically, federation will be used between coherence clusters in separate Kubernetes clusters, which are generally geographically dispersed. But for ease of demonstration, we are installing two separate coherence clusters within the same Kubernetes cluster. The demonstration will also show one of the clusters enabled with active persistence and how the persistence data is available and automatically recovered after deletion and recreation of the cluster. Firstly, we are going to install the Coherence operator with log capture enabled, which will install Elasticsearch and Kibana, as well as configure FluentD to scrape logs from Coherence and Coherence operator pods. Let's view the installed release. Let's also view the pods. We can see the Coherence operator pod as well as the Elasticsearch and Kibana pods. Next, we install two coherence clusters, primary cluster with a release name of cluster 1 and secondary cluster with a release name of cluster 2, both of which are configured with federation. Primary cluster is also configured with active persistence. Let's look at the cache configuration and operational override for the cluster. The cache configuration is a standard federated scheme where we are setting the topology to active, which is defined in the override file. We also set the port for federation to 40,000, which we will reference in the Helm install. The operational override defines the active topology and cluster participants. The property values will be overridden via the Helm install. Let's take a look at the YAML for the primary cluster. The key point to note is that the properties for primary cluster host points to the cluster 1 coherence headless, which is a DNS address within the Kubernetes cluster which maps to all cluster 1 pods. This is also set up similarly for cluster 2. As mentioned before, A typical federation scenario would normally be between two different Kubernetes clusters. In this case, we would create a service object to expose cluster members' federation port to an external IP address. Please refer to the Kubernetes documentation on how this can be achieved. We can also see the user artifacts image that contains the cache and operational configuration we just showed. In this scenario, we have active persistence enabled, which by default will create a Kubernetes Persistent Volume Claim to store Coherence active and snapshot persistence data. You can also manually specify the volumes, allowing you to set specific storage types. For example, if we are using OCI, or Oracle's Cloud Infrastructure, the default storage type of the persistent volume claim would be block storage. This is fine for snapshot location, but active persistence requires the lowest latency and would benefit from a different storage type, for example NVRAM. Let's install the primary cluster. Let's now look at the Helm releases and then the pods. Let's look at the persistent volume claims. Because we enabled persistence on primary cluster, we can see the persistent volume claims which are bound to the pods. Next, we install the secondary cluster with the release name of cluster 2. This configuration is the same as cluster 1, except the different cluster name and persistence is not enabled. We can now see all of the three releases, being the Coherence Operator, cluster 1 and cluster 2. Now we will view the pods. We can see that both the clusters are running. Now we will port forward the Coherence Extend ports on 20,000 for primary cluster and 20,001 for secondary cluster. We are using port forward just for this demonstration, but normally you would use a load balancer for Extend connections in a production environment. Primary cluster, secondary cluster. Next we will connect via CoQL to the primary cluster on port 20,000 and the secondary cluster on port 20,001. First, let's select a count from the caches to confirm there is no data present. We can see we're connected to port 20,000 and the result is 0 for primary cluster. We're connecting to 20,001 and the result is also 0. Now we'll insert data into the primary cluster. We can see the data is in the primary cluster. We'll go to the secondary cluster now and do a select. We can see the data is there because it has been federated. We can update the value for key 1 in the secondary cluster, and this will be reflected in the primary cluster as federation is set up as active-active. Let's also insert a new value with key 2 and value 2 into the secondary cluster. Let's go back to the first cluster and do a select. We can see the updated value for key 1 is there and also the new value for key 2. Next, we will open Kibana to view the logs captured from the clusters. When we start Kibana and go to the dashboards, we can see there are a number of dashboards preloaded by the operator. For this demonstration, we will take a look at the All Messages dashboard. We can now see logs from both clusters, as well as we can refine and drill down via cluster, host, message level, or thread. For example, if I wanted to see D6 messages, I filter for them. This will update all the visualizations, and I can further refine this by selecting Cluster 1 Coherence 1 host. I can then remove them by clicking Delete. Please see the Coherence Operator Management screencast for more information on Kibana and log capture. Next, we will delete the primary cluster, which is Cluster 1 Helm release. This cluster has active persistence enabled, which means the Kubernetes Persistent Volume Claim will remain after the Helm release is deleted. We'll confirm that all the pods are gone. Only cluster 2 pods remain. We'll view the persistent volume claims, which you can see are still there. Next, we will reinstall cluster 1, which is primary cluster, and the previous persistent volume claim will be attached. Active persistence will then load the cache data from disk, effectively recovering the cluster to its state before shutdown. Let's wait for the pods to become available. We can now see that cluster 1 is up and running. We can see also that the CoQL session was disconnected when the pod went away. We'll now issue a select. We'll see that the CoQL session is reconnected to cluster 1, and we can see the data is still there as it's been recovered from the previous state via active persistence. This concludes the demonstration. If you would like more information about the Coherence operator, please visit github.com/oracle/coherence-operator. You can also view the Coherence operator documentation and detailed samples available at oracle.github.io/coherence-operator. Also, feel free to join our operator and Coherence channels on Slack by using the instructions in the documentation. Thank you for your time.